Hello, my name is Major Derek Worth, and for this project, I explore the use of machine learning to improve position estimates during automated aerial refueling. Since GPS and other signals-based approaches can be jammed or denied in contested environments, the DoD is exploring computer vision approaches that give machines the ability to see like humans can and predict in real time the relative position of objects in relation to itself with only image data. If successful, this will enable autonomous agents to perform automated aerial refueling without a human in the loop, giving our military a new capability of persistent, uninterrupted, and self-sustaining air power. The computer vision technique I'm currently experimenting with produces predicted probe-to-drogue vectors from the perspective of the receiver aircraft as shown here. The vector error for this technique averages near zero in all dimensions, but the standard deviation of the error grows as the distance between the camera and the object increases as shown here. In other words, predictions are noisy. The plot on the left depicts the true position of the drogue in relation to the receiving aircraft leading up to contact point over time, while the plot on the right shows the predictions. Zooming into these predictions, this plot shows the error as well as the acceptable threshold. So for this project, my research question was, can denoising autoencoders remove the noise from these predictions, resulting in error within the acceptable threshold shown here, plus or minus 7 centimeters at contact? The data for this effort was generated during several simulated aerial refueling approaches. In simulation, 9 cameras were mounted on the tanker and 3 on the receiver as shown here. Each camera automatically adjusts its viewing angle to capture an optimal scene for probe-to-drogue vector estimates. Along with the truth, the estimates from these 12 cameras comprise my dataset. The final dataset used here contained 3 labels, 36 features, and over 150,000 observations, all of which were stored as floating point numbers. Literature shows that autoencoders have the ability to remove noise from data. This effort attempted to exploit this capability by deploying an autoencoder to remove noise from the original 12 probe-to-drogue predictions, resulting in a more accurate single prediction. To measure success, this effort implemented 5 different solutions for comparison. First is the simple average of all predictions, which is used as a baseline for the autoencoder to perform against. In addition, this effort explored a simple, dense network with 36 inputs and 3 outputs, a simple CNN with 36 inputs stacked as 12 length 3 vectors and 3 outputs, an autoencoder with the same inputs as outputs, in other words, 36 predicted values in, trained on those same 36 values out, and lastly, a denoising autoencoder with 36 predicted inputs and the truth vector repeated over the 36 outputs. While implementing the previously mentioned solutions, this effort applied a variety of hyperparameters to include network depth, layer and bottleneck width, number of epochs, loss and optimizer functions, dropout, and various other parameters like stride and kernel size for the simple CNN. Each model was trained until performance leveled out. The metrics used to measure success were the overall average and standard deviation of the probe-to-drogue vector errors across all 5 solutions in X, Y, Z, and vector magnitude, specifically for the test dataset. For the solutions with 36 outputs, the average was computed, resulting in a single 3-length vector. The final results for the 5 solutions are shown here. Overall, the simple averaging solution produced the best predictions. However, the denoising autoencoder was able to slightly outperform the simple average in the X and Y dimensions at the trade-off of poor performance in the Z dimension. Experimentation showed overfitting was not an issue in this effort, and regularization techniques like dropout were not only unnecessary but also decreased overall model performance and accuracy. Autoencoders with small bottlenecks took too long to train and didn't perform well. These next 2 slides show the error in predictions for the first 4,000 observations in the test set. Comparing the plots, we see that the dense, convolutional, and even autoencoder networks produce some instability in predictions, as evident by asymmetric error and large error spikes. However, the denoising autoencoder did produce less error, which is visible in these plots. In conclusion, denoising autoencoders did provide some error reduction in probe-to-stroke vector predictions. However, the error reduction wasn't significant or consistent enough to justify using it over the simple averaging approach, especially since it traded off error reduction in the x and y dimensions for an increase in error in the z dimension. Future work could include implementing recurrent layers, since this is a time series dataset, and perhaps adding convolutional layers inside the autoencoder to further reduce error. This work contributes towards my AFIT research by giving me tools to improve my computer vision position estimation technique. This concludes my project, and thank you for listening.